Even me sometimes I make bad mistake lah. Let's get started. Okay, our topic is flow rate and equation of continuity. Okay, we have covered fluid statics. Okay, done. Fluid statics done, and we have learned about buoyancy and Archimedes. Okay, done. So now this is under fluid dynamics. Okay, flow rate and equation of continuity. Okay, this is first part. Today we will cover part 1 and part 2. Part 2 will be Bernoulli equation. Okay, Bernoulli. Okay, or Bernoulli principle. Okay, what is flow rate? Okay, what does it mean by flow rate? So imagine we have a pipe containing, inside the pipe is fluid. Okay. Okay, so this volume of fluid, or we say water lah, or fluid lah, fluid. Okay, we can draw like this. Okay, this is the volume of a fluid. Okay, fluid, and of course it continue lah. Okay, but we only want to specify this volume of fluid. Okay, this part only. But here it is moving. So there is whole of water, whole of fluid. So flow rate says that flow rate equal to, okay, flow rate is Q, Q equal to the volume divided by time taken for it to pass. Okay, that's it. The volume time taken for it to pass. Okay, let's say it is 20 meter cube per 5 second. So we say that the flow rate is 4 meter cube per second. So volume per unit time. Okay. So V is our volume, T is time. Okay, in second. Volume is meter cube SI unit. So we know that volume also. Okay, here is volume. Okay, volume equal to A times length, or D in this case. In this picture, it is put as D, so it's okay. So now A times D will get us this volume. So we can write like this, AD over T. So D, since it is length, okay, it is length, not diameter, it is length. So length divided by T is speed. Okay, length divided by T is speed. Displacement divided by T equal to speed. So flow rate, if you are given time and volume, so it's easy lah. But sometimes they don't give the volume. They give us area and speed. Okay, so we can find using either this or this, depend on what are the info given to us. Okay. So flow rate is defined to be volume of fluid passing an area per unit time. Okay. Fluid passing an area per unit time. Okay. Now, imagine we have a pipe here. Okay. So common sense tell us that, okay, at position 1 and position 2, the flow rate is the same. Common sense, because we have this pipe and it flows. Okay, common sense. So at point 1 and point 2 are the same flow rate. Okay, why? Because this is ideal fluid and this is conservation of mass. So when mass is conserved here, the mass will be the same here because mass is conserved. When mass is conserved, volume will also be conserved, be equal. So flow rate here and here and here is the same. But this is common sense. But if the pipe is like this, then maybe we think, oh, it will be a bit different. No, it will be the same. Okay. Why? Because mass is conserved. The concept here, mass is conserved. Of course, that is in ideal condition. Okay. So, of course, area is changed, but Q is the same. Q1, Q2. Remember, Q equal to A times speed. Q is the same, but area change. Speed change. Okay. So, this is valid for incompressible fluid, which is ideal fluid, and laminar or steady flow. Turbulence, we cannot use. Okay, you have to learn deeper in the fluid topics. So, equation of continuity states that Q1 equal to Q2, or we can write like this. So, if I ask you in the exam, okay, what is equation of continuity? You can write this straight away. If you write this part, I will only give you partial marks, not full mark. Partial only, partially. Give this, okay? And write. Or if, because this is the same, you can write like this, okay? And state that here, okay? A is area and V is speed of fluid. If I ask you what is equation of continuity, please give this and this. Okay. This one is only partial marks. Okay. So equation of continuity is derived based on the fact that mass can neither be created or destroyed. Okay. Mass is conserved. That is the fundamental behind the equation of continuity. Okay. So you can also put it into sentence, okay? You can say that flow rate at point 1 and 2 or point rate at any point in the pipeline is the same. Same things, same as this equation. So now, because we know Q equal to A times speed. So what happened if A is changed? What happened to V? Okay, so we want to study the relationship. So imagine we have that visual, okay. Point A, okay. A1, A2, A is smaller here. A is bigger here. Is velocity at point 1, point N2 is the same, okay. Just refer to formula, we get like this formula, okay. Imagine, let's say area here is 5. The speed here is 4. Okay, 4. Speed 4. So we get that flow rate is 20. Flow rate, but according to equation of continuity, okay, flow rate anywhere in the pipe, flow rate is the same. So meaning here, although A2 is smaller, let's say A2 is 2 meter square. Let's say, okay, 2 meter square. This is 5 meter square, this is meter per second. So what is the value of V2? Because the total must be 20, Q2 20, so this must be 10. So here you see when the speed decrease, when the area decrease, the speed increase from 4 to 10. Okay, so vice versa. Okay, so based on equation of continuity, speed increases when cross-sectional area decreases. Okay, and same thing lah. Speed decreases when cross-sectional area become bigger, let's say. Okay, so it is indirectly proportional. Now example. Okay, suppose water flowing through pipe diameter 1. So diameter make sure in meter. Okay, not cm. Why they give us diameter? Because equation of continuity have A. Okay, A here. So A pi r square. D over 2 square pi r square. So first diameter is 0.01 meter, okay, with a flow of 2 meter per second. So now D2 is 0.03 meter, V2 is, we don't know, fine. Okay, sorry, this is wrong. Not new flow rate, new speed. Okay, new speed. So just apply the formula, okay, find V2 and so on. Okay, very easy. Okay. Try, although this is easy, sometimes things seems easy, but when you try to do it on your own, sometimes we make a mistake. We maybe careless and so on lah. Okay, right. So sometimes we tend to forget to put square here. Okay, it is normal lah. Even me sometimes I make that mistake lah. So try to do it on your own. Okay. Finish first part. Okay, lecture note, I haven't uploaded it yet because I want to find if there is more example to give you. Okay, maybe this afternoon I will upload it. Please take a look, or in the evening. Okay, now we go to next subtopic, which is Bernoulli Principle. As you can see in the picture, okay, here, definitely we can find flow rate, okay, if we know the speed and the area. And as you can see, okay, water or piping, it is not always put in the same flat height, same flat surface. So sometimes it comes from top of the hill and then go to the ground and then go back up, okay. Sometimes it is like that. So piping, the shape of piping, the how they build the piping is different from one place to another. It serves different purpose lah. Okay. So what we want to know now, we are going to learn the equation that we use to relate the pressure and the speed of the water. Okay. And if height, okay, if the ketinggian height can contribute something, okay, to the pressure or to the speed. Okay, now some basic knowledge before we proceed. Okay, in school you have learned that atmospheric pressure is given by this, okay, or 0.8 atm or bar or this. You have learned in school. So SI unit always this. If you are given this unit, you have to convert to SI unit. Okay. How to convert it? Please check the books or just Google it. I don't want to go into detail because that is just simple mathematics. Okay, we go on physics concept only. So we know that in pipe, fluid flow because of there is difference in pressure. Point A to point B, fluid can flow from A to B because there is different in pressure, meaning pressure gradient. So since pressure here is higher, it will move here. Okay, it will move here. Fluid will move from left to the right. So we say pressure gradient causes fluid to flow. Now, pressure in fluid, okay, could be considered as energy per unit volume or energy density, okay, or also called confined energy. So meaning pressure is also a type of or a form of energy. It is energy per unit volume, okay. Last week, one of your friends asked me about strain energy per unit volume, okay. Okay, strain energy per unit volume, half times stress times strain. His question is like this, okay. Since the unit for this, okay, I use in lecture note, the unit is joule per meter cube. Okay, joule per meter cube. He asked me, okay, very good question. Okay, very good question. I don't remember his name, unfortunately, but it is very good question. Okay, the unit is joule per meter cube. Okay, joule is for energy, but here, according to this formula, okay, strain is unitless. Okay, no unit. Okay, because it is changed in length, let's say, divide by length. So unit is meter, meter you cancel off. This stress, okay, stress is F over A, or pressure. The unit is Pascal, or maybe Newton per meter cube, meter square. Okay. How come suddenly I turn this into this? Because the unit here only, this is a half, no unit. Okay, here the unit is Pascal or Newton per meter square. Okay. This is unitless. So how come this unit become this unit? Okay. Very good question and brilliant question. Okay, now, I'm going to show you, to prove to you that pressure is actually energy per unit volume, and so energy per unit volume is joule per meter cube. Meaning, unit Pascal is the same as here. I'm going to show you this. So pressure and energy per unit has the same unit actually. How? Okay. Now we know that P pressure equal to F over A. Okay. F also equal to MA. Okay. M is your mass, A is the acceleration. So the unit for MA is M is kilogram, acceleration is meter per second square. Area is meter square. So the unit now become pressure. Now this is the unit. But of course, we don't like to write like this. Okay, we don't want to write like this. So people introduce the word Pascal. Okay, it is easier, or Newton per meter square. So actually we can write this unit. Okay, no problem. Just follow all the unit, respective unit, individual unit. Okay, now energy. Energy is E equal to mc square, the famous Einstein formula. Or you can try on your own, E equal to mg h. Try to find the unit. Okay, you will get this unit and this, you will get the same unit. So E equal to mc square, m kilogram, c is your speed of light, meter per second square. So now the unit will be like this. Okay, kilogram meter square per second square. Still, this is not the same as this. Why? Because this is energy. What I said is energy equal to, pressure equal to energy per unit volume, not energy. So still not the same. So how we are going to show to prove that? Energy per unit volume. So we just divide by volume. So now, what is unit for volume? This is unit for volume. So we expand, we get like this. Okay, kilogram, meter. This, you see this, is equal to our pressure unit. So that's why the strain energy per unit volume has got this formula. Okay, joule per meter cube. Same like Pascal, we don't want to write all this, so we said this, joule per meter cube. Energy, energy is joule. Okay. Now we prove that pressure is also a form of energy. It is confined energy. So now imagine we have scenario like this. Okay, we have a pipe going to higher ground. Okay, going higher ground. So we learned that in the first part, we say that mass is conserved. As a result, we learned that Q1 equal to Q2, and it remains it holds. It is valid also in this situation. It remains valid. Okay, it is not contradictory. Yeah. Okay. So, but now this mass conserved. But now we have about conservation of energy. Okay. Bernoulli principle or Bernoulli equation state is related to conservation of energy. It states that, okay, conservation of energy states that energy at any point is conserved. Energy here, 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 all are conserved. Okay, energy at any point is conserved. So, since energy at any point is conserved, energy per unit volume is also conserved. Either here, it is the same. Or here is the same. So, this is how to write it is in a mathematical way lah. Okay. So what are those energy that present in flowing fluid? Okay. What are the energy? Okay. First, okay, imagine this is our volume of fluid moving. Okay. This bulk or this volume, okay, sorry, this pipe is located at higher ground. Okay, this is just for the sake of discussion. Height can be changed. It can be 0 if you want. Okay, but this for discussion. Okay, imagine we have water flowing. Okay, this bulk or volume of water, okay, when it moves, meaning it has kinetic energy. Okay, and this is formula, simple. This mass is this mass of volume of water. Okay, this formula. And since it is at higher ground, we can say that it has potential energy given by this formula. Okay. And just now, we have proven that energy, pressure is also a form of energy. So we say that energy due to pressure of liquid in the specified volume is here. Energy, PV. Why V? Because we specified this volume. Okay, now energy per unit volume is like this. Kinetic energy per unit volume. Sorry, So divide by volume. So we get density. Mass divided by volume is density. Potential energy per unit volume, we get like this. Divide by volume, we get density. Energy, okay, due to pressure per unit volume, we get this pressure only. So these are the energy present in the fluid that flows in the pipe. Okay, all of this energy, 3 energy. Okay, so now we say that Bernoulli equation or Bernoulli principle states that the sum of the pressure, kinetic energy, and potential energy has the same value at all points along a streamline. This is the Bernoulli equation definition. Please memorize and understand this. Okay, this is still conservation of energy because value at all points the same. Okay. So sum of energy per unit volume, okay, per unit volume, 0.1 equal to 0.2. So this is the sum, okay. Okay, this is the sum that this is pressure, this is your kinetic energy per unit volume, this is your potential energy per unit volume, equal to 0.2, okay. Or because it is equal, we can also write like this, just like your equation of continuity, you can write like this. Okay, constant. So when I ask you what is definition of Bernoulli equation, you have to write this. Okay, you have to write this or this, and make sure to tell me what is P, what is V, what is rho. Okay, although I know, but I want to see it. Okay, because that is exam. It shows that you know. Okay, it shows that you know. Okay, so now let's play around with the formula. Okay, So this formula, okay. Imagine we have a pipe, okay. For the sake of simplicity, at the moment let's say we say that it is at the same level. Okay, now let's say the pipe, okay, suddenly becomes small. Okay. We know by formula of equation of continuity, okay, when there is change in the area, then speed will be different. Okay. So now imagine, let's say the pressure here is 100 and this part here is also 100, let's say. Okay. So here is 0, let's say, because we cancel off. And suddenly, let's say the pressure here, okay, is suddenly 50 pressure here. But it must be equal. Here it is 100 plus 100. Total up to 200. Now, this is 50. So meaning, this term, in order to balance value of 200, must be 150. When this value, whole value is 150, meaning the speed here is higher. Okay, speed here has to be higher compared to this. Okay, it has to be higher. So we say that when pressure decrease, the velocity will increase, provided this is at the same level. So when pressure decrease, speed must be increased to balance the value of 200. Okay, so that is, we just try to play it around without proper calculation. Okay. So higher pressure regions have lower fluid speed and lower pressure region have higher fluid speed. Okay. And in all the same, actually the same things. Increase in the speed of fluid occurs simultaneously with decrease in pressure. Okay, decrease in pressure, increase in speed. Okay, same thing. Or a decrease in fluid potential energy. If you play around with this, you will see it. Now, please go back and look at the example. Okay. Once I have uploaded the lecture notes. Please go through. Okay, this involves Q to AV. Okay, so sometimes the question, they don't give you this value V. Okay, so you have to find using this equation. Okay, but this is rather straightforward. Okay, and remember, flow rate, the unit must be volume per, meter cube per second. Okay, cannot be liter. So everything should be SI unit. Okay, this also should be SI. So you have to convert it first, not L big. Liter is L only. Okay. Oh no, yeah, L, big L. So convert first, easy. Just open your book and read through the book how to convert, or just Google. Okay. But try to understand this concept of how to use the equation. Okay, I have shown everything. Okay, please go through, please do it yourself. Please check maybe if I miscalculate. If I do, let me know. Okay, and this equation, okay, just we cancel off because it is at the same level. Okay, and you will get this answer. Okay, very easy. Just go back and try to calculate. Okay, maybe maybe if we do practice a lot, we can overcome our carelessness. Sometimes in mathematics we tend to do things carelessly. So by practicing a lot, inshallah we can overcome that problem. So sometimes it happened to me. Sometimes I forget to square here. and square here. So it does happen. Huh? So go back and try and check whether my calculation is correct. So that's it for today. Inshallah, I'll see you again tomorrow, my last lecture, and hopefully you can understand so far of what we have learned. Okay, thank you so much. Thank you for your time. Thank you for listening. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Waalaikumsalam. Thank you, Doctor.
Thank you, Doktor.